Okay. So I didn't assign this as an actual lab for you and I because we need to go through it and you need to actually understand what's going on. So this is a photogate. Yeah, and we got a bunch of them, and they're pretty classical. I mean, this was the poop like 20 years ago. So basically, a light goes from one end to the other, and one is an emitter and one is a detector. So it's a little light, LED, usually infrared. It's the same kind of light used on old style television remotes. So it goes through, and there's a little door to open and close it, and then there's a detector here, and it knows when that light is blocked. Block, block, block. So it knows right away on, off, on, off. And then this is called a picket fence. And what you'd usually do is you'd stick a picket fence on an object. And as it traveled through, it would go on, off, on, off, on, off, on, off. And then you'd say, I know how wide the black area is. So if I know how wide the off area is, and I know how long it's blocked, then what do I know? Exactly, I know the speed. So it's like on, off, on, off, on, off, on, off. It's like, okay, I know the time it took that it was blocked, and I know the distance of these things, so I know the speed. And what this is for is if you drop it, then the speed gets smaller and smaller, the time gets smaller and smaller and smaller. So the speed gets smaller and smaller and smaller, and you very quickly get a graph that gives you the acceleration. Okay, so far so good? Okay, so that's what you'd use it for. You'd either drop it through the photogate, and that's actually a lab we used to do until I just hated these things. And the reason anyway, and then they could also put them on top of a device like a car, and it would go through the photogate. And we actually might still do that. I gotta figure out how much work it is whether it's worth it, because these are super finicky. They used to be the only thing you could use 20 years ago. But now we have cameras that we can go to the hundreds of a second, and the cameras just work away. They're just easier to use because they're just like, they work. These, they sometimes work. But anyway, that's what a photogate is. And the reason I mention it is you will still see questions dealing with a photogate. It's like a photogate is used, and you're like, what is that? Taking pictures? No, this is a photogate. All right, are we comfortable so far? Now, in simulation, what's happening is a index card is set on top of an object, in this case, a little car, little toy car. And we know the size of the index card, so we know how long it should be tripped, or if we do know how long the photogate's going to be tripped, then we can come up with velocity. Okay, so far so good? Are you comfortable with me so far? Again, if I talk too fast, please let me know. Your teacher has given you a toy car that will accelerate with a constant acceleration, because acceleration is always constant. In physics, it's constant positive, constant negative, or zero. It's never a changing acceleration, because that's rocket science, and we don't do rocket science. You have set up two photogates to help you determine the acceleration. An index card has been placed on the roof of the car as a way to trigger the photogates with an object of known size. Mid-time is a time when the car is the average velocity for the gate. It happens at the exact midpoint in time between the gate being blocked and unblocked. So in other words, the car goes through, mention the cards right here, it goes blocked, mid-time, unblocked. Blocked, mid-time, unblocked. After you've determined the acceleration of the car at the end, uncheck your book. Okay. So, click on the index card, take measurements of the width of the card. You will need this value to find the velocity of the card. That's pretty easy. Just go click. How big is it? Well, 16.5 centimeters, which is how many meters? 0.165. So, the distance of the card is 0.165 meters. Were we cool with this? Are we comfortable with this number? Go back. And go back. There we go. Okay. Logger Pro. So Logger Pro is the software that runs these things. We have a new program called Graphical Analysis, which runs on the website. Logger Pro is the stuff that runs on the little computers that we would normally use. Yeah. Again, 20 years ago, Logger Pro was the poop. Everyone's like, oh, you got vernier? Awesome. When I started teaching physics AP 10 years ago? Maybe. Anyway, I was like, we need these things. And he's like, oh, okay, I'm a new principal. Here's some money. We got all sorts of cool stuff. Click on the green button. We'll start the Logger Pro collecting. So here we go. Boom. Boom. There we go. Click the gas pedal at any time. I think we just press it once. Boop. Boop. All right. So we have two states, blocked and unblocked, blocked and unblocked. Okay, so we have two states, blocked and unblocked, blocked and unblocked. And from this, we can get velocity. So far, so good? All right. So let's calculate the time of the blocking of the state 1 and state 2. So this is going to be state 1, it goes through state 1, then it goes through state 2. So the delta time is what? This is u. Do I need to blow it up? No, up. There we go. It's 0.13. Again, we've got, we're subtracting, so we should all use all the 1319? Okay. Yeah, since when we subtract, we use all the significant digits that are available to pass a decimal. Okay, and you would expect that time 2 would be smaller because it's accelerating first through time 1 through time 2, so it should be going faster in time 2. So what's the time 2 time?
0.086.
860. Is that right?
Yeah.
Seconds and seconds. Okay, so this gives you two pieces of information. It tells you the average velocity as it goes through the first gate, and it tells you the average velocity after it goes through the second gate. So let's go ahead and find those.
V1 is 1.251.
251 meters per second. And V2?
1.92.
1.92. Just 1.92?
Yeah.
Okay. Meters per second. Cool. So yeah, it's speeding up. Now the midpoint is, or the mid time, is the time that averages these two. So if this is the blocked versus the unblocked, the mid time is the time right in between those two. So mid time 1 and mid time 2. So find the average of those, please.
First mid time is 4.697.
7.
And then the second one is 4.958.
0.958. All right. So if you're comfortable and you have a pretty good idea what's going on so far, you don't care what's happening in the future, but you have a good idea, pretty good idea of what's going on so far, give me a thumbs up. Okay, let's repeat. So cars going through a first gate, blocked, unblocked. It's accelerating the whole time with a constant acceleration. Next one, it's still accelerating, blocked, unblocked. So what we have here is we have a first velocity and a second velocity. And we also know the difference in time between those velocity changes. Does that make sense? So this is the middle of the first block. This is the middle of the second block. Why do we have to use the middle of the first block and the middle of the second block? Why can't we use the time between the first block and time when they first open? It is moving, but we have what we measured here is important. Why do we have to use the middle of the card instead of the time at which it's blocked and the time at which it exits? Why can't we go blocked minus blocked or open minus open? Well, maybe you should just discuss it. Take a few seconds, take a minute, and discuss why we actually need to know what the mid time is. Go for it. Because
it's between the state and so. Well, yeah, how many times the same for clothes?
This will be a use to your average velocity.
okay, who thinks we might know why we have to use the mid time? The time between when the card blocks it and when it's open again. What do you got?
I mean, I guess like if you use like open or close, if you start in the beginning of your app, depending on if you're measuring an open or closed gate, it'll be different for each one. Like if you use the mid time, it'll be the same if you're measuring open or closed. And it's more reliable. Right?
Well, if you use the open,
Like if you open one
it's
time,
going to be slightly different than the closed.
Yeah.
Because it's in front of the card.
yeah, totally different.
The open, sorry, the blocked is going to be smaller than the open. But specifically, what have we measured in taking the average time and the distance? The average velocity. And when does the average velocity happen? In the middle of the card, right? So if it's going this direction, here we're going to call this V blocked, and here we're going to call this V open, and right in the middle we have V average. Because the card is accelerating the entire time. As the card goes through, unless you're talking about something approaching the speed of light, it stays the same size as it's accelerating. So if you were to rank these, you're like V open, V average, and then V blocked, again, because it's moving that direction. What kind of mathematical symbol would you put in here? I'll give you a hint at the same in both cases.
Like greater than?
Greater than? So greater than is greater open or greater average?
Greater average.
Greater average? We have some disagreement. Because it's accelerating the entire time. The blocked velocity is the lesser of the three. The open velocity is the greater of the three because when the front of the card gets blocked, the object is still accelerating and the back of the card, it's moving faster than at the front of the card. So because it's blocked, unblocked, and it's moving faster, so it's like, I'm going 3 meters per second. When I finally get through the card, I'm going 3.5 meters per second. Is that clear? Can you wrap your head around the concept?
Yeah.
So since the card is speeding up, the front block speed is less than the back open speed. And since we are measuring the average, we need to know what the time is right there. So what is the difference between these two? 0.261 seconds. And that is the time between that and it's going the wrong direction, but this still works. Okay. V average there. So that is the time difference between when the first card passes, the middle of the first card passes, and the middle of the second card passes. How are we doing? So now what we have is an average velocity and the change in time. If we have an average velocity and a change in time, what do we get to calculate? Acceleration, which is that's what we're going to do. So I don't think there's anything to put in here.
No.
So go ahead and determine what the acceleration is from when it goes this way. It's going to have a constant acceleration, and what is that going to be? The numbers we have up here.
So 0.56.
Wow, that's huge.
2.56.
Where did you get those numbers?
So
Subtracted 1.251 from 1.92, and
Okay.
I divided that by 0.269.
Okay, so delta of 1.92 minus 1.251
Yeah.
over the mid-time,
Yeah.
delta t, of 0.261.
Mhm.
And that returned an acceleration of
2.56.
56 meters/second. Let's see how we did. Can we get a consensus on this? We're comfortable with this number? Okay. Vic, here, doing your acceleration. Name its class. Class. And your acceleration you got was 2.56. Moment of truth. Yes! You are right. Well done. So that's cool. Getting numbers right is great. But what's more important is you understand why we had to do all this. Again, if we did this in lab, nobody would get the correct numbers because those things just don't work right. They work great. They were okay 20 years ago, but if we did it with a camera, we could do it. So what's happening is the card is going through the first photogate. Boop, boop. It's accelerating the entire time. Boop, boop. It's the same card. Boop, boop. And if we know the time here and the time here, we know the average velocity it goes through the first gate, and the average velocity it goes through the second gate. And if we know that average velocity and that average velocity, we know the delta V, the change in velocity. So now all we need to know is the time between this average velocity and this average velocity. That's why you get the mid-time. You average the time in between, and then subtract, get the mid-time. From here to here, we have a change in V. From here to here, we have a change in A. That gives us acceleration. All right. Questions? Okay. Open it up with your neighbor. Work through it again and see if you get. Should I erase all this stuff?
Sure.
Yes. So go ahead and do it again with your neighbor and take a few minutes and see if you get the same thing that we got. I think this is where I could turn off the video. I think Bennett and Jillian got everything they needed. Bye, Bennett and Jillian.
California, do your clam boys.